Hello, everyone. Thank you for joining us. I'm Kathy Wells, Editor-in-Chief of Equipment Today and OEM Off-Highway. Welcome to today's webinar, Steer-by-Wire, Designing Safe, Scalable Steering for Modern Machines, presented by David Schulte, Jonathan Thomas, and OEM Off-Highway. Today's session is being recorded and will be available on demand this week at oemoffhighway.com. A couple of tips before we get started. Our presentation today will feature slides with live audio from our presenters. You'll note that your view within the system is customizable, so please feel free to adjust the layout and engage with different windows to meet your viewing preferences. You may submit questions for our presenters at any time during the presentation using the Q&A section on your screen, and we will answer as many of those as possible. And last but not least, please be sure to check out the related content section for some additional information and resources there. Today's webinar is sponsored by Parker and will explore selecting, designing, and validating steer-by-wire architectures. Parker is a Fortune 250 global leader in motion and control technologies. For more than a century, the company has been enabling engineering breakthroughs that lead to a better tomorrow. Our presenters today are David Schulte and Jonathan Thomas. Gentlemen, thank you both for being here with us today. At this time, I would like to hand over the controls to Jonathan to get things started with some introductions and then begin the presentation. Jonathan?
Sure. Today's webinar, we're going to talk about four main topics here: evolution and applications of steer-by-wire and off-highway machinery, functional safety for steer-by-wire systems, system architecture options for steer-by-wire, and key steer-by-wire componentry. So over the last 100 years or so, the design of industrial equipment has had quite a journey, including trying to figure out how to steer such large equipment. Early machines started with very mechanical steering systems, consisting of gears and linkages that required a lot of human effort to steer the machine. But in the 1950s, hydraulic power steering was introduced and really launched a new era for steering design. That really continues today amongst a wide variety of different types of off-highway machinery. These conventional hydraulic steering systems are pretty well established and typically consist of some kind of hydraulic orbital valve that meters the flow of hydraulic fluid directly to the steering cylinders, which turn the vehicle. Again, hydraulic steering has been around a long time, and we believe that it should continue to be a great solution for a lot of different off-highway applications. But what we're seeing though evolve is these migrated kind of the market migrating to these hybrid type of systems where a supplementary electric valve is now introduced, and that's receiving a signal from a GPS system that really runs in parallel to the conventional system. It's typically doing something like augmented steering or some type of special feature steering. And today we're seeing more and more OEMs migrate, take the full step towards steer-by-wire. And this is really removing the hydraulics from the cab altogether. So we get rid of the orbital completely, and our steering signals are communicated exclusively by wire. So there's some nuances though in steer-by-wire systems that are impacted by the level of functional safety that may be required, with these kind of types of electrical systems. So we're seeing two basic steer-by-wire system architectures evolve. The first one, we'll call it basically like a fail-safe system. When a failure is detected, the vehicle alerts the operator, with some kind of warning, and then, safely slows the machine to a stop so that those repairs can be made. The other is, what we call a fail-functional system, where two full channels of independent and redundant systems exist. In the event of a failure here, the vehicle again alerts the operator that something's wrong, but you can continue to steer the vehicle. My colleague David, he'll talk more later on about functional safety and how OEMs decide which architecture is best for them. So what does a steer-by-wire system typically include? Essentially, there are three new critical items. The first is what we call a steering input device, which is typically either a joystick or a steering wheel. This input device sends a steering signal to a controller. This could be the vehicle controller or some kind of standalone controller. And then the controller commands some sort of output device, typically an electrohydraulic valve to drive the steering cylinders, or it could be an electric actuator that physically, turns the vehicle. In steer-by-wire systems, since the steering wheel is no longer mechanically or hydraulically connected to the system, we saw some early adopters that had complaints about the overall steering feel for operators. But over the last 25 years or so, input devices have evolved to reproduce this controllable tactile feedback that simulates the feel of these legacy hydraulic systems, that can recreate, steering end stops and allow OEMs to redefine, how operators interface with the machine. So several industries have, already adopted steer-by-wire. Parker's experience with steer-by-wire dates back into the late 1990s, where we supported forklift manufacturers to adopt electric powertrains and then kind of migrate from a hydraulic steering system to these fully electric steer-by-wire systems. Since then, steer-by-wire has been deployed in several other markets, including ag, mining, precision construction, marine, and several other niche off-highway vehicles. So why are so many OEMs looking at steer-by-wire for their next vehicle? We here at Parker kind of identified these four general themes that seem to have a major influence. The first is integration with autonomous systems. So many OEMs are trying to offer some sort of semi-autonomous machine function, where the machine is doing the work, including steering the vehicle by itself for some portion of time, without an operator. So steer-by-wire allows these software-based systems to directly control the steering with, again, those inputs typically coming from a GPS signal, instead of the operator. So this capability helps, make autonomous functions like auto guidance and precision maneuvering and remote operation all possible. The next theme is this one of machine design flexibility. So by removing the mechanical steering column and the orbital, you can improve the operator's line of sight and free up cabin space to deploy either more flexible cab interiors, new operator control designs, or even things like seating, where you can adopt a seat that swivels maybe 180 degrees to face the direction of travel. That might be useful in some applications. Mechanically disconnecting the steering wheel also allows OEMs to select between various steering input devices to kind of suit their target market or their customer's preference. So again, typically a joystick or a steering wheel. Or you could even relocate the steering wheel to the seat armrest, for example. Since we're, again, by wire, we have a lot more flexibility. Also with steer-by-wire, OEMs can more easily design like a base steering system architecture that they can use across several vehicle platforms, and then fine-tune each platform with its own steering performance or steering identity. So this kind of approach can significantly reduce the engineering development time for future vehicles. The next theme is customizable steering response. So all of the steering characteristics can be modified with software. If you don't like the way it feels, we can change it. So for example, steering can be programmed to be more sensitive for these precise low-speed maneuvering, and then less sensitive for stable high-speed travel. I'd say more generically, the steering feel can be, optimized for different work functions. So, if you want a specific function to feel a certain way, you can kind of, gives you the capability to cater to that specific need, which therefore can improve, operator productivity. By disconnecting the steering wheel from, the mechanical system, steer-by-wire also isolates the operator from jolts, noise, and vibrations that might come transmitted from the terrain. So, this can improve comfort and reduce, operator fatigue over, really long shifts. The final theme is potential cost reduction. So, in steer-by-wire systems, there are typically fewer components, which results in a lower assembly cost for the OEM and typically a lot less hydraulic hose routing and potentially some lower warranty for hydraulic related leaks. So as more and more markets look at steer-by-wire, we see the volumes increasing, which should continue to reduce the upfront investment for OEMs.
All right, folks, I'm going to call your attention to our first poll here where we're asking a little bit of a review of what we just covered. What are your primary drivers to evaluate steer-by-wire for your future machines? If you don't mind, everybody take a quick second to review these options and make your selections here. You are able to make multiple selections if you have multiple drivers. So keep that in mind when identifying your primary choices here. And do be sure to hit submit once you've made your selections. Just walking through our options here, is it that integration with autonomous systems? Is it machine design flexibility, customizable steering response, potential cost reduction, or is it something else entirely? If you are selecting that other category, we'd love to have you share those other drivers and what they might be. So using the Q&A tab, let's have you offer that information to our presenters so we know what it is that you're looking at there. Just type in any of the other considerations into that tab and hit submit. For our poll, we will give it a few more seconds here. Again, don't forget to hit submit so we're able to count you in our results. Get in those votes and we will get things moving. Okay, I think that maybe ought to do it. All right, guys, I'll pass the controls back over to you to take a look at these results.
Awesome. So it seems like there's a good response, a good mix of motivations, and I'm sure that again a lot of these factors come into play for a lot of companies. So as I mentioned earlier, the feel of early steer-by-wire systems was a major concern for some OEMs, and so we think that its importance really shouldn't be underestimated. The tactile feedback of steer-by-wire systems, really should emulate the feel of these conventional hydraulic systems, while remaining safe and stable and quiet. Most equipment manufacturers are deploying what we see as what we call resistive feedback control, using some sort of controllable electric rotary brake. So the steering resistance can be controlled in real time by modulating current to the rotary brake to produce a specific torque characteristic, which can be customized for unique operating conditions. So the rotary brake can be tuned to enhance the HMI, the human to machine interface, in ways that would otherwise be challenging to really implement in maybe legacy systems. For example, the first icon there is center resistance. So this is the idea of creating some kind of physical detent during the steering wheel motion to inform the operator of some kind of center position. So that might be really valuable in a situation where you're looking over your shoulder, trying to steer the machine, and you really want to know, where the center position is. The next icon says steering pressure feedback. So this is, aligning the steering resistance with the steering cylinder pressure. So as you're, building cylinder pressure, you're making it tougher to steer. And so it's kind of creating a steering experience that's much more familiar, for the operator with these legacy hydraulic systems. But you can also address the steering resistance to account for any potential latency in some of the downstream like hydraulic circuits. So, without any tactile feedback, you might turn the steering wheel faster than what the hydraulic circuit could keep up with, where the vehicle wheels are reacting, slower than the steering wheel command. So, that could lead to a dangerous over or understeer type of situation. So again, having tactile feedback might be valuable in that situation. The third icon is this adjustable lock to lock, or being able to change the steering ratio for different operating functions. My best example is in the marine market, where in normal steering mode, it might take you 3 or 4 turns to go from full left to full right. But with steer-by-wire, boat manufacturers can now offer their customers a docking mode option, where you press a button on the boat and you can change the steering ratio, whereby boaters can get like full articulation of the outboard engines in less than 1 turn of the steering wheel, which dramatically simplifies the process of docking a boat. So in that market, this was a highly valuable feature to improve the boating experience. The final icon there is position velocity feedback, or offering the ability to change the resistance as your steering position changes, or when the steering wheel spins at different speeds. So when you're turning the wheel and you're approaching an end stop, do you want the end stop to be nice and firm, or do you want to gradually kind of ease into that end stop, making it gradually more difficult? Different OEMs have different perspectives on what a nice steering performance feels like. So being able to cater to all those different expectations is another advantage for steer-by-wire. Major point is that all these features are tunable to the OEM's preference. But there are also newer technologies that are being developed with what we'll call active feedback, where motors are integrated into the system to add energy. So these motors can help to move the steering wheel. We're not just using a braking torque anymore. A motor to add energy to again provide this active return to center functionality, and really a more sophisticated automotive-like steering feel. The motor could also move the steering wheel during like autonomous operation. OEMs so far seem to have different opinions on whether the steering wheel should be moving or not moving during autonomous mode. So again, having an active device would be more advantageous for customers that do want to see the steering wheel move. And I'll talk more about both of these products later on.
All right. Good afternoon, everybody. This is David Schulte. I'd like to take a few minutes now to talk about functional safety and how it relates to steer-by-wire. So functional safety is a very broad topic, and the first comment I'll make is there's nothing specific about steer-by-wire that functional safety takes into consideration. So functional safety is a broad subject. It's not a steering specific topic, and there are a lot of standards out there. And my goal today is to talk about a few that are very common, especially when we assist our customers with steering systems. But I'm not intending to, let's say, go over every single standard out there, because there's quite a few. So like I said, functional safety, the reason why it's a common subject when it comes to steering is because functional safety standards cover safety-related parts of control systems. And I would say in general, nearly everyone would consider steering systems to be a safety-related control system. These standards can be a bit daunting because, as I said, there are several of them out there. My best description for maybe someone that doesn't deal with functional safety standards on a daily basis is that they're very generally written, and they really essentially provide a best practice guideline for how to design a system. So they're meant to cover a wide range of machinery, so they're not there to point out that a wheel loader or a tractor has to have X sensor or Y sensor. They're there as really a design guide. And as I mentioned, there are several out there. I would say as a general statement, most of these standards start with some sort of a hazard analysis. Then once an OEM has performed a hazard analysis on that function, it then gives some guidance as to what type of architecture would be needed to realize whatever level that hazard analysis came up with, and then define some level of component or system robustness that an OEM would need to use. The last statement I'll make is, there are jurisdictions in the world where complying with functional safety standards are required, but that's not a universal statement. So obviously, for when you are designing and building and marketing your machine, you should understand what type of requirements are required in that region. So that's a kind of, to take it one step down, a number of functional safety standards really originate out of Europe. The machinery directive compels OEMs to follow functional safety standards when they're doing their design process. In the United States, where maybe most of us are based that are on the call today, there's no specific requirement pushing you to abide by these. But what I have noticed with a lot of our global customers is that because they're, number one, that best practice design, and because there are several jurisdictions internationally that require conformance with these standards, it's best. A lot of OEMs take that step that they decide they want to design a machine that can be sold globally, and they're looking for essentially one common design across, let's say, across regions, as opposed to maintaining different design concepts. Certification is something that is always can create some uncertainty. A number of functional safety standards essentially allow you to self-certify if you have the expertise on staff. There are, of course, consultants and what are called notified bodies within individual countries, both in Europe and in the U.S., that you can go to for help to, let's say, gain confidence that you're in compliance with these standards. So for today, I'd just like to talk about only a couple standards, just to run through some examples of how one may choose to design a steering system. ISO 13849 is by far, I would say, the standard that our team supporting off-highway equipment, this is probably the most cited standards that our customers come to us and let us know that they are attempting to conform with. ISO 25119 is very similar. The risk assessment is a little different, but the ISO 25199 is specific for ag and forestry tractors. ISO 5010 is not a safety standard, but it is a steering standard. And I throw this up here just to highlight that ISO 5010 does refer back to functional safety standards like ISO 13849, just to tell you how even non-functional safety standards can sometimes reference back, asking OEMs to conform with, let's say, ISO 13849 or 25119. So with the theme being a discussion around designing a steering system, really the first step in any of these complying with these standards is to perform a risk assessment on your machine, and more specifically the subsystem that you're designing for. So in the case of steering, what is typically done is machine builders who should be experts at the machine that they build. They may also bring in maybe expert operators or people that apply the machines in the field, discuss the type of risk scenario that would be appropriate to evaluate. And then also probably most important is to really document boundaries around what your analysis is trying to accomplish. And so this is an example of the risk tree from ISO 13849. It would start with a consideration for, let's say, injury to a person. This could be the operator. It could be a bystander. You really should define what you are attempting to review with your risk assessment, how frequently that person would be exposed to the risk scenario, and then what possibility there is to avoid. So I'll make a statement that, of course, this is the machine builder's decision to figure out what this, let's say, the outcome of the risk assessment. A performance level of the letter D is a very common outcome that OEMs come to us as Parker and say we are trying to achieve performance level D. So there's no person or entity out there that is going to tell you what your machine should achieve, but the reason I've circled and I'm kind of using D as an example today is that is a very common performance level that OEMs are attempting to achieve. So once you've determined what performance level is required, there's a lot of different factors, and I'm not going to go through every single detail, but once you've figured out, let's say, the level you're trying to achieve, you then have to decide your category architecture. You have to find components that have a specific level of mean time to dangerous failure. You have to design a diagnostic coverage, how you're going to read and diagnose errors in your system. And then if controllers are involved, the probability of dangerous failure per hour, it's kind of a lot of words there, is related to the micro. And we'll get to that a little bit later. So just at a high level, like I said, there's more details to this. I'm keeping it pretty high level for today. The category architecture would define, let's say, the input, the logic device, and the output. Does that need to be redundant? Do you need a certain level of diagnostics and sensors associated with it? So the category architecture, once you decide your performance level, you then should identify what type of architecture you want to choose to comply with that. Mean time to dangerous failure. So this is a unit that's measured in years. And typically, if you're buying these components, either component or subsystem from a supplier, that supplier should be able to provide this information. And then diagnostic coverage. This is not just the sensors, but also the software used to measure and diagnose failures in a system. So I like this table. It's a little more clear than I think that graphic from before. But like I said, we decided our goal for a steering system should be D. And so to do that, what we're going to look at is a category 2 architecture, which you can see that you're able to achieve that. You're able to achieve a performance level D with a level 2. That would also point you to a high level of mean time to failure, and then a medium level of diagnostic coverage. So as far as the architectures go, the first 3 architectures called out in 13849 are what I would say these would be non-redundant architectures. So they have various levels of robustness. Category 2 would, of course, you can see with those dotted lines, it represents that the need for feedback and checking of the input, the logic, and the output along the entire channel. The lower two categories would be fully redundant. So you have two complete legs of independent control. And then, like I said, to keep with our discussion today, I'm going to focus, at least for this exercise, on a category 2 system. The MTTF data, again, I'm not going to get too into the weeds other than the MTTF value that you're trying to achieve is a function of all the devices in the system. And so for us, we were targeting a level of high. For diagnostic coverage, again, not trying to get into the weeds with the calculation, but just to reinforce, like I said, it's not just we've selected our components, we've selected the sensors that are used to diagnose those components, but we also have to make sure the software is designed so we're doing the right thing when we detect a failure or we see that performance has fallen. So for that category, the PLD that we're trying to achieve, we needed to find this medium level. And ISO 13849 does have an annex that talks about different strategies for achieving the right diagnosis for your system. So lastly, if you go back to this chart from before, you may have noticed at the far end here, it references a SIL rating. So this typically is associated with some sort of a controller, a control device. And so to achieve D, it is looking for this probability of dangerous failure rating to be these very low numbers shown here. And then you can see that even in the standard, it calls out SIL2, which is a safety integrity level that's called out by, let's say, other safety standards like IEC 61508, for instance, or sometimes another one that focuses on that is IEC 62061. We've talked about the hardware. 13849 also references the V model style of developing software. And really the takeaway from this is documentation is key. So when you're setting out to design your system, you want to document what the system should do in detailed software specifications, break that down to lower level pieces that are well documented, and then documenting your test procedure, documenting that you've tested your test procedure, and at the end, what you validated matches the requirements. So good practice for developing software for, of course, a steering system or any safety-related system. And with that, I'll jump into kind of a few different examples of, let's say, fully designed systems. So we went through that exercise looking at a PLD system. So in this case, what I've shown here is a performance level D system. So we've selected a category 2 system like we've gone through. So we have an input device, a logic device, and then an output device. And then that dotted line again represents some level of feedback. So your architecture, this is one of the Parker TFD components. So we have a version of this unit that has 2 feedback sensors that give you in-range failure detection as well as short to power, short to ground. So we're satisfying that diagnostic portion of the system. Of course, we've chosen a fail-safe controller, which is a SIL2 certified controller. And then in this case, we have a spool sensor for feedback, and then we have an energy off solenoid that in the case of a recorded failure, we're able to turn off the steering function altogether. So this would be another example of a PLD system. In this case, it would be a category 3 architecture. So there's a lot of reasons why you may want to choose this. I referenced ISO 5010 earlier in the presentation. That standard actually identifies vehicles of a certain threshold may need to be able to retain steering function in the case of a failure. So that could be a driver for someone to choose a fully redundant system. In this case, we have an input device that actually has 4 output channels. 2 can be read by each controller. two of the fail-safe micros controllers, so that one could if one were to fail, you have a backup. And then in this case, we actually have a fully redundant dual channel hydraulic valve that's able to turn off one whole leg of the control circuit and still be operational for the second leg. I think that brings us to our second poll question.
Okay, taking a look at our second and last poll for you today, what level of functional safety does your company envision for your equipment? We'll have you select one of the following. Is that category B, basic safety principles, category 1, single channel no diagnostics, category 3, single channel periodic diagnostics, category 3, redundant channels, periodic diagnostics, and category 4, redundant channels, fault tolerant. Everyone, please take a quick second to make a selection here, and please be sure to submit so we're able to count you in our results here. We'll leave this up for just a little bit longer to get those votes in and tally things up here in just a second. All right, to keep things moving, we'll close out in just a second here. Everyone be sure to hit submit. All right, and I will take, I'll hand things back over to the guys to take a look at the results and keep things moving.
Great. Thanks, Kathy. It looks like this result kind of shows that this category 2 and category 3 are really the dominant drivers, which is kind of in line with what we would have assumed. Category 4 showing, think about category 4, we're getting into more like automotive type of safety and requirements. So we can imagine that there's definitely some spaces out there, but so good. We appreciate your feedback. In this last section, we wanted to kind of take the time to talk about a few of the various products that Parker Hannifin offers for steer-by-wire, starting with our rotary input device. We call it a tactile feedback device, or a TFD. Again, the TFD has two primary functions: to communicate steering position changes, and then number 2, to create this programmable, variable steering resistance back to the operator. And so how much resistance you need is typically related to the size of the steering wheel as you try to recreate a firm end stop in a full left or full right steering condition. So remember, in steer-by-wire, there are no end stops. So larger steering wheels will produce a larger moment arm, and therefore you need a larger rotary brake to kind of recreate a nice firm end stop feeling. With smaller steering wheels, you can use smaller rotary brakes. In our portfolio, we have rotary brakes ranging from 5 Newton meters, which is used extensively in the material handling market, where again, they tend to use smaller mini wheels on those vehicles. We also have a 12 Newton meter brake. This is commonly used for like automotive size steering wheels. And then finally a 20 Newton meter brake, which was originally developed for larger marine steering wheels. So every TFD that we produce uses some proprietary technology called magneto-rheological fluids, or MR fluids. I'll talk more about MR fluids on the next slide. But really the most safety critical aspect of the TFD is to produce an accurate, reliable, and safe steering signal. So we use non-contact Hall effect sensors, typically 2 for redundancy, sometimes 4 for quad redundancy, really depending on the functional safety requirements for that application. But the steering signal can be sent as either an analog signal or a PWM signal, or through the CAN bus. We use J1939 protocol. And some of our TFDs have integrated controllers, where we've already developed the algorithms to control the MR rotary brake, leveraging signals from the CAN bus. So hopefully this reduces the software burden on our customers and makes our devices more plug and play. So I mentioned that one of the enabling technologies in our TFDs is the use of MR fluids inside of the device to dynamically change the steering resistance in real time. So these MR fluids were actually developed by Parker Lord back in the 1990s and come in a liquid or powder form. So in the presence of a magnetic field, these fluids change their properties from a fluid to a semi-solid. And those properties are proportional to the strength of the magnetic field applied. So in a small magnetic field, the iron particles will align and create a small amount of resistance. Similarly, in a large magnetic field, the shear strength of those magnetic bonds increases and produces a larger braking force. So in the TFD, we can modulate current to the device to change the steering resistance in real time and to simulate end stops at full left and full right of a steering turn. Those end stops are really the only time where you actually need the peak torque capability of the device, where you're trying to lock up the rotary brake to create a nice firm end stop. The other rotary input device in our portfolio is actually still under development, but we call it a force feedback device, or FFD. And the FFD adds a small 2 to 3 Newton meter servo motor to a 12 to 16 Newton meter MR brake, along with all the steering sensors and integrated controls. So in this configuration, the MR brake provides the end stop control and the resistive torque, while the servo motor provides this return to center function, as well as other active capabilities for wheel traction feel or on center control or vehicle system warnings. Think of like rumble strips for lane departure. And it also could be valuable in like a multiple steering system synchronization. So vehicles that have multiple steering wheels, do you want each of them to kind of move together, when you maybe in some certain operating mode? The end result is really a product that offers this automotive-like steering feel for an industrial vehicle. The motor is direct drive, so there's no gear mesh noise or backlash. We've done all the soft work again for you. So knowing when to command the MR brake versus when to command the motor. Again, really trying to make this device plug and play. We've seen certain competitors working on similar technology, but they're using a much larger motors, and we feel that our approach of using a small motor significantly helps with the functional safety analysis, since we can claim an exception to the risk that, hey, there's this large motor that might inadvertently fail and overpower the human. That sounds risky, but by using a small motor, a human can still fight back in that situation and really maintain control of the vehicle.
And this is where I'll jump back in. So what Jonathan was going over was Parker's offering on the input device side. As far as the logic controller, let's say a device that Parker has to offer is our ICANN family of controllers. So we have a version of our control system that is non-SIL rated, and then we have a version of our control system that is SIL rated for those higher performance level requirements. We are SIL 2. We have this control family comes in a family of 3 different sizes depending on the type of IO that you're looking for. And typically, or when OEMs opt to use this family of controllers, they're also utilizing our development tool, essentially our ICANN design control software for building your projects, and then ICANN run and simulate, which are part of that tool chain that helps develop a system. One comment I will make is over the last few years, as Parker has been supporting more and more steer-by-wire projects, we have pre-built several applications in our ICANN environment that really does help in getting a steer-by-wire machine up and running quickly. We pre-built these blocks to be able to read our input devices, handle some suggested level of diagnostics, and then control our steering valves, as well as reading and input sensors like chromaxles and whatnot. The comment I'll make is these tend to be somewhat building blocks. What we've found is seems like every steering application, OEMs are looking for some nuance or something unique. Steering a tractor is very different from steering a forklift, so there's a lot of things that you have to take into consideration. Parker, also recently, we've recently added a few valves to our lineup. We've had our steer-by-wire 110 valve in the market for 4 or 5 years now. But Parker offers a purpose-built steer-by-wire hydraulic valve. We think that the differentiating feature in these valves is that it's a full dual-channel electrohydraulic Category 3 valve. So what that allows you to do is you can maintain those 2 channels that we've talked about before to meet a Category 3 architecture, and both of those are fully EH. So there's not necessarily a need to have the hydraulic traditional rotary steering valve in parallel. So these 3 valves are range from 110 liters of flow up to 450 liters of flow for some really large, think about the big mining machinery. And then, of course, we publish all of the relevant data that OEMs would need to comply with their functional safety standards that they're choosing to comply to. And with that, I believe that brings us to an end. We do appreciate your guys' interest in our webinar, and know that through both the components and engineering expertise, Parker is there to help build that customized steering application that you may be looking for. And that's all I have.
All right, guys, up next is our Q&A session, and we've got several questions to get in front of our speakers. So at this time, I'd like to go ahead and kick things off. We will start with, let me grab our first question. For your TFD product, you mentioned that MR fluids are a key enabling technology for smooth steering feel. Can you explain more about why that is?
I can go ahead and take that. I guess a key aspect of MR fluids is really how quickly the fluid can change its properties. So there's other rotary brake designs out there in the marketplace, but those designs typically bring a rotor and a stator together electromagnetically, which can grind and produce a noticeable and unpleasant sensation in your fingertips, these wonderful little sensors. Our TFD designs, we put a layer of this MR material between the rotor and the stator, which can adjust the steering stiffness much more quickly and smoothly without all that abrasion, which in turn just kind of results in a much more pleasant experience for the operator. So Parker Lord invented MR fluids back in the 1980s and 90s, and still, I think today we're the largest commercial producer of MR fluids worldwide. You might recall MR fluids that gained notoriety in these kind of controllable shock absorbers, or think of them as linear brakes. Really, there was the name MagneRide that was popularized for primary suspension in high-end cars. Parker Lord also builds MR shock absorbers for seat and cab suspensions and off-highway equipment, but they're premium products because the MR fluid reacts quickly, and it changes its damping rate in real time to the prevailing terrain, to kind of provide this best-in-class comfort. So our TFDs use this same technology really to provide a premier steering experience. So hopefully that answered the question.
Thank you, Jonathan. Okay, up next, how commonly are CAN-based input devices used in such systems?
I'll start. For the input devices, I'd say, steer-by-wire for us started with forklifts. I think that there's a different level of technology that's used in different marketplaces. So I'd say the majority of our products that we sell are still analog or PWM signal products. But I think with the evolution of especially as we get into higher grade off-highway machines, there was this clear feedback from the marketplace that there was a desire to have the steering signal on the CAN bus. So we try to include CAN-based product in our offer, and I'd say we're seeing still growing interest in CAN-based solutions for the marketplace. David, do you have anything else to add there?
Yeah, one certainly every application, they may have a preference for machine architecture. On the functional safety side, if let's say you're using already a functional safety controller or SIL2 controller, there's sometimes the desire to keep all that logic on a single processor and simply be reading signals in from your input device rather than having a separate processor out on the input device. So there's some advantage. Some OEMs see that as an advantage when they're developing their architecture. So that may be a reason why analog devices may never, transition fully to CAN. But I wouldn't say there's any right or wrong way to do it. We just want to be able to always offer both options.
Okay, great. Next up, this attendee says, hello, thank you for the presentation. Have you ever designed and integrated the steer-by-wire type steering system for an 8x8 or 6x6 military vehicle?
If you want to start there.
Yeah, we haven't we've had interest from different customers about military applications. I don't know that we've commercialized or gone into production with any specific military vehicle, though. But clearly, an input device would be an option for that type of system. I'm not sure about the rest of the system, David.
So Parker has, I would say, I don't know about that specific wheel configuration, but certainly Parker has assisted customers with multiple steering axles. So I'm I guess maybe reading between the lines a little bit that maybe on the 8x8 or 6x6, multiple wheels are steering. But the short answer is yes, we have spec'd out and tested, let's say, multiple steering axles with multiple valves that can either sync together in some desired way, or maybe not the case in the military vehicle, but certainly like crab type steering, where you may want to be able to select between crab steering a machine, or maybe like, let's say, a tight bend radius where your front axle steers right and your rear axle steers left. So I would just say, and it's a comment I made before, is we've supported a number of steering applications, and one overriding theme is it does seem like every application has some sort of nuance that we have to put our heads together and try and find the right solution that meets with that application.
Well said. Okay. How about another question? Next up, we have you worked with ISO 26262 for automotive functional safety, perhaps in particular with non-road mobile machinery and heavy-duty trucks that are on-road certified? And they also note as ISO 13849 is not acceptable for on-road use.
Yeah. Jonathan, I don't know if you want to make a comment. I can certainly comment a little bit too.
Yeah, I'd say our strategy so far, we've seen, the evolution of steer-by-wire start in the off-highway market, and so now we're quite, conscientious of the evolving trends in on-highway, in automotive, and those technologies will eventually get pushed into truck. Which comes first, I don't know, but it is a different set of functional safety standards. And so, I guess as our history is more of a industrial equipment type of company, we don't have necessarily, qualified products yet to meet all automotive requirements.
Yeah, and I'll add to that. Certainly, I'm aware of the standard. I'm certainly aware of the comment. I certainly get that. Parker motor controllers. So we have a number of other divisions that produce components that comply with the on-road standards, the 26262. Our team, so our background is certainly focused on off-highway equipment, which is why for this presentation and our focus for off-road is around that 13849. So I hope that does answer, but yeah, definitely our immediate focus, at least for the steering, is on the off-highway market.
Thank you, gentlemen. We have time to squeeze one last question in here. Is the development environment, aka tool chain, for the Parker logic controls approved or recognized by notified bodies as a safe system?
Yeah, that's a good question. So in the ICANN environment, our functional safety toolbox, we do have ways of sectioning off areas of control logic for, let's say, a functional safe, like a performance level D type level. Now, what I can say is, while we have built blocks that are designed for steering, because every application that we have supported has had some level of nuance or customization that's desired, what we would then advise the OEM to do is bring that either to a notified body, or that OEM may be comfortable enough to, let's say self-certify. But as far as, because we've had such a diversity of interest in different applications, we don't have, let's say, a standard block that has been certified.
Okay, everybody. Unfortunately, that does it for our time today, which brings our webinar to a close. I'd love to thank our speakers, Jonathan and David, for their insights and expertise here today. And just to our audience, we did receive a ton of great technical questions. And I know our speakers would be happy to get those answered offline, since we've just run out of the minutes here. Attendees, you will be receiving an email from us with access to today's playback and presentation, but please also feel free to visit oemoffhighway.com to check out more on this topic and browse other topics in our bank of educational webinars. And before you go, please be sure to check out the related content section for some additional information and resources there from Parker. Thank you again to our speakers, and thank you all for taking the time to join us. This concludes today's program.
All right, thank you.